In this series of lectures, I aim to describe the path integral method in quantum mechanics. And if time permits, I will go on to talk about statistical mechanics, applications of path integrals to statistical mechanics, as well as quantum field theory. But let us first try to understand path integrals in quantum mechanics. And we will begin by describing the object that we want to calculate using path integrals in the long run. We will first try to understand this object within the framework of our familiar quantum mechanics. This object is what is called the propagator. And for the time being, we will stick to one spatial dimension, and of course we are going to talk about non-relativistic quantum mechanics in 1D. And the central equation which describes our system here is none other than, of course, the Schrödinger equation, or what is often called the time-dependent Schrödinger equation. Of course, the name is a bit of a misnomer, or slightly misleading at least, because this is the Schrödinger equation. The time-independent Schrödinger equation really is a sort of derived result which comes out of this. But as you all know, the time-dependent Schrödinger equation goes like this. The Hamiltonian operator, some operator which describes your system, acting on the wave function, which for our one-dimensional system will be minus h cross square by twice m, second partial derivative with respect to position, plus the potential acting on psi. This will be equal to IH cross del psi del t. Or we can rewrite this in a slightly more formal and simpler looking fashion. Let's correct this. In this form, IH cross del del t minus the Hamiltonian operator acting on psi is going to give me 0. Okay, now this equation is a linear first order differential equation in time. And because it's linear and first order, basic differential equation theory tells me that if I know the value for this function psi x at some time ti, this equation should be able to tell me the function psi of x at some later time t. This is something which the equation should be able to calculate for me. What is more is that because of the linearity of this equation, the connection between psi of x at time ti and psi of x at time t should be linear. What that means is that we should be able to express the wave function at time t at the position x as a linear superposition of the values which the wave function takes at different x primes at the time ti. Of course, when I superpose them, I have to add up over all x prime, and x prime being continuous, this becomes an integral over x prime from minus infinity to plus infinity. And the coefficients, the weights which different positions x prime contribute to the final x, that will be a function of 4 variables, x and t on one hand, and x prime and ti on the other. Now this particular function, the k which is sitting here, the name k stands for the word kernel, which is a mathematical term. This is called the kernel, or perhaps more familiarly the Green's function for the time-dependent Schrödinger equation. And this is what we call the propagator in quantum mechanics. It essentially gives you the probability amplitude of finding the particle at position x at time t, given that it was at position x prime at time ti. So it's easy to see that this propagator will satisfy an equation which is very similar to the Schrödinger equation itself. In fact, it will satisfy its own version of the Schrödinger equation, and that equation will look like this. same operator IH cross del del t minus the Hamiltonian, this time acting on kxt x prime ti. Notice that this is of course an operator which is acting only on the variables x and t. X prime and ti are just constants as far as this equation is concerned. This gives me I times h cross times a delta of x minus xi x prime and another delta of t minus ti. It is this particular form which tells you that the propagator is really the Green's function for the Schrodinger equation. Not only that, it has to satisfy one more important condition, the boundary condition. And the boundary condition will be this: k at x ti plus epsilon x prime at ti in the limit when epsilon goes to 0 plus. Remember, all this works when the time t, which here is ti plus epsilon, is more than the time ti. So here you have only a one-sided limit, epsilon going to 0 from the positive direction, and this is delta x minus x prime. So if you start with this partial differential equation and this initial condition, what the situation is when t approaches t prime, you should be able to figure out what the propagator is. But before we go on to calculate the propagator or express it in other forms, let us just first verify whether this really works at all. That is, if the propagator obeys this differential equation here, this one, and this boundary condition, does it really lead to a solution of the time-dependent Schrodinger equation for psi? To check whether the kernel or the propagator really gives us a solution to the Schrodinger equation, let us just directly apply the differential operator I h cross del del t minus Hamiltonian on psi of xt. But before that, let me just write down the equation once again. Psi of xt is basically this quantity integral over dx prime, and what we want to do is apply the operator I del del t or I h cross del del t minus the Hamiltonian on this thing, and notice the integration is over x prime, which has nothing to do with the variables which are here in this particular differential operator. The variables in this differential operator are t and x, which is there in h, but neither x prime nor ti features among these variables. So this operator can happily go inside the integration, and not only that, once it's inside the integration, it will completely ignore this, which is a constant as far as the operator is concerned, and will only attack this, the propagator. And as we assumed right now, or as we proposed, IH cross del del t minus the Hamiltonian acting on the propagator gives you IH cross delta t minus ti delta x minus x prime psi x prime ti dx prime, and this immediately gives me psi x ti, that's the integration over x prime done, times an IH cross, but also multiplied by delta t minus ti, and since this equation works when t is more than ti, this immediately gives me 0 because the delta function, delta t minus ti, vanishes when t is more than ti. Well, that's not the only thing that we have to check. We have to also check whether our boundary condition works, but that's sort of easy. If you start with our formula for the wave function and take the limit where t approaches ti, always keeping in mind that t is more than ti, then what you are doing here is that in this integral you are taking this t and moving it closer and closer to ti, but from the limiting value we have assumed for k, which remember is up here, if t is just a bit more than ti, or t is ti plus epsilon, where epsilon approaches 0 from the positive direction, this becomes delta of x minus x prime, and then the integral of delta of x minus x prime. So this gets replaced then by delta of x minus x prime in the limit when t approaches ti from the positive direction. And when this becomes delta of x minus x prime, integral of that after multiplication by the wave function at x prime ti just gives me the wave function psi at x comma ti. So the integral of the kernel with after multiplication by the wave function does satisfy both of our conditions. It satisfies the partial differential equation which we call the Schrodinger equation. It also satisfies the boundary conditions, or the initial condition, sorry, not the boundary condition, but the initial condition on the Schrodinger wave function. Now for a time-dependent Hamiltonian, H, if H has no explicit time dependence, we can find an explicit form of the propagator in terms of the eigenfunctions phi n and the eigenvalues En of H. So these are my H eigenfunctions and these are the H eigenvalues, and just for simplicity's sake I am assuming that the eigenfunctions and eigenvalues are discrete so that they can be labeled by n and you can write sums involving them. So of course what we are claiming here is H acting on phi n is En phi n. So that's one property we are demanding. We are also demanding, this is elementary quantum mechanics, that the phi n's are orthogonal, that they have to be, but we are also demanding that they are orthonormalized. So phi n star phi mx dx integrated over all space is delta mn, and on top of that we are demanding that they form a complete set. All of this is elementary quantum mechanics, which is, if you did this sum over all energy levels, you will end up with the Dirac delta x minus x prime. This really is an old-fashioned way, or there is a wave function way of writing down the completeness relation, which is the Kedbra phi n, the projected to the state phi n. If you add them over all n, you get the identity. This relation and this relation are exactly equivalent to each other, at least in one-dimensional quantum mechanics. Now, with this background, let me point out that what we can do is we can start with our initial value, psi of xti, the wave function at time ti. We can of course expand, because of the completeness of the wave functions phi n, I can expand them in a sum where the an coefficients need to be found out. How do you find out the coefficients an? You just use the orthonormality of the phi n's, and then you end up with a very simple formula for the coefficients. An is simply nothing but phi n star x psi x t I dx. By the way, I could have also done this at time t instead of time ti, then of course you would have ended up with different coefficients an. For the timing, the an's are the coefficients which psi x ti, the wave function at time ti, has when expressed in the basis given by the wave functions or energy eigenfunctions phi n. Now that we know psi x ti is of this form, psi xt is pretty easy to write down. Let me just change the pen color a bit. Psi xt, this is the wave function at time t, can be easily figured out because, once again, the time evolution which is dictated by the Schrodinger equation is linear. So all the phi n x's will individually evolve in time independently, and the linear combination will evolve into the corresponding linear combination, and we know how energy eigenstates evolve in time. They just pick up a phase factor. It is a minus in I times energy into the time interval by h cross. So that's what psi of xt is. So if you know the coefficients an, you can use that to directly find out the wave function at time t. So this is again elementary quantum mechanics. So this is what we have. Psi at xt is simply all the states are going to be summed over. It's a minus I en t minus ti by h cross and phi n x. But now we know that ans can be written down in terms of the original wave function. So we just use that. So an is nothing but phi n star. And now we have to be a bit more careful. Now we are going to write ans as an integral over position, but we cannot use the label x for the integration variable here, because this integral, of course, is being done over an independent variable, which is a dummy variable of integration in this case. So I just call it x prime. So phi n star at x prime, psi at x prime ti, this is my an, times e to the minus I en t minus ti by h bar times phi n x. Now what you can see is that we are very close to our final result. We need to be able to express psi of xt as psi of x prime ti times the function of xt x prime ti integrated over all x prime. So all we have to do is interchange the order of the summation over n, which is being done last here, and the integration, which is being done first. If I interchange and do the integration after I do the summation, I end up with this result. Psi x prime ti is independent of n, so it comes out of the sum. So does dx prime. And inside the sum, what you are left with is this. All the independent pieces are left inside the sum. Phi n x, it is a minus I en t minus ti by h cross. So we have an explicit formula for the propagator at our hands here. This thing in the bracket is nothing but the propagator. So the propagator works out to be kxt x prime ti is nothing but sum over all possible energy eigenvalues, phi n star x prime, phi n x, times e to the minus I en t minus ti by h cross. And let me point out that although I've written this as a sum over all n, this of course makes the simplifying assumption that the spectrum of the Hamiltonian is discrete. It could of course also have continuous and discrete parts, or could be a continuous spectrum. So what we mean by the sum here is really that it's a sum over the discrete part and an integral over a continuous part, if any. But as you can see, if we know all the eigenfunctions and eigenvalues, all the phi n's are known, all the en's are known of the Hamiltonian, then the propagator can be explicitly written down in terms of that. That doesn't necessarily mean that it's easy to calculate the propagator. It does mean that we have a formula which we can fall back upon to derive or define the propagator for us. So we have established that we can write the propagator from x prime ti to xt as a sum involving the eigenfunctions and eigenvalues of the Hamiltonian H. But there is one factor missing here, and that factor is what captures the fact that this propagator works only in the forward direction. That is, it gives you the wave function psi at xt from the wave function at psi x prime ti, provided t is more than ti. And for that we need one extra factor which goes in here. That's a theta function. So this theta function is something which all of you are pretty familiar with. This is theta. X is defined to be 1 for x greater than or equal to 0 and 0 for x less than 0. So this is what the theta function is. So this ensures that our propagator only propagates wave functions forward in time, or it causes effects, or the resulting wave function is formed after the cause. So this is also called the causal or retarded propagator. Retarded because the effect occurs after the cause. So the time t is after the time ti. That's what the theta function ensures. So just to see how this works out, let's try to now directly verify whether this propagator k that we have written down in terms of this wave functions and the energy eigenvalues, this really satisfies the boundary condition that we talked about and the differential equation that we talked about. The boundary condition is sort of easy. If you just put in t approaching ti from above, remember it's approaching from above, that's why this is equal to 1. And then when t gets very close to ti, this factor here becomes 1. So you are left with just this term here, just this piece. Phi n x, phi n star x prime summed over n, and by completeness that's nothing but delta of x minus x prime, which of course was a boundary condition. So this propagator satisfies the boundary condition rather trivially. Now going back to the differential equation, let's see how we can establish that. What we need to do, of course, is apply IH cross del t minus h, this operator, on the kxt x prime ti. So this is what we need to calculate and show that this is equal to IH cross times delta x minus x prime delta t minus ti. Let's do this in steps. Let's first apply IH cross del t on the kxt x prime ti. Now let me just show you what we had here. This is kxt x prime ti. So if we do the derivative with respect to time, the derivative will come from two places. The theta function here is time dependent, which of course suffers a jump at t equal to ti. That's the only place where there's a jump. And otherwise it's a constant. So the derivative of the theta t minus ti term simply gives you a delta function. Delta t minus ti, because that's exactly something whose integral will give you back the theta. And the rest of the sum. Let me just write out the sum here. Phi n x, phi n star x prime times e to the minus I e n t minus ti by h cross. That's one term. Of course, that's not the only term. Get one more term here because this factor here, the en t minus ti, also depends on t, and its derivative will give you a non-zero result. So we'll get theta t minus ti, then the sum, and most of the terms in the sum of course will not be affected by the derivative. Phi n x, phi n star x prime, these are all independent of t, so they will not be affected. The exponential of course will just give you the exponential back. But there will be one extra piece which is something which comes from the derivative here, and that gives you minus IEN by h cross multiplied by the IH cross which is there in front. This just simply gives you an EN. So this is what the time derivative of the propagator gives you. What about the Hamiltonian acting on the propagator? Acting on k x t x prime ti. That actually is pretty easy, because most of the factors here will not be affected by the Hamiltonian at all. The Hamiltonian, of course, is an operator which depends on x. So the only term here which depends on the x is the phi nx. And phi nx is a Hamiltonian eigenfunction. So when you sum up over, or when you apply h on phi nx, what you get is En phi nx. The rest of the factors are simply not touched. So you should realize that when the Hamiltonian acts on the propagator, the term that you get is exactly the same as the second term that you obtained when IH cross del del t was acting on the propagator. For the del del t, the En term came from the exponential. When the Hamiltonian was acting, the En term came from phi n, but ultimately they give you the same term. So when you subtract the two, that is when you apply IH cross del del t minus the Hamiltonian on k x t x prime ti, the result is only the first term here. Now that looks like a pretty complicated term, but let me point out that the delta t minus ti ensures one thing. If t is not equal to ti, you are going to get a 0. So it does not matter what the rest of the sum is when t is not equal to ti. When t is not equal to ti, the whole thing is 0 anyway. But when t is equal to ti, that's the only place where you have a non-zero result from this term. At that value of t, the rest also simplifies substantially, because you are just left with this thing. Phi nx, phi n star x prime, because the exponential, when t is equal to ti, that's the only point, remember, where this function has support, where it's non-zero, the delta function, I mean, this factor simply becomes 1. So you just live with 1 here. But what is this sum? As I said a while ago, this sum is nothing but the delta function in x. So you get IH cross delta t minus ti into delta x minus x prime. So there you have it. Once you incorporate the theta function in the result for k, that is here, once we put in the theta function here, I now have a propagator which actually satisfies the differential equation that we have imposed on k. It also satisfies the boundary condition. So this is our actual propagator. In what follows, what we are going to do is we are going to take t greater than ti throughout, so that theta of t minus ti, this factor, will always be equal to 1, at least in the subsequent part of this video. So we are not going to write that down explicitly. That is just for a bit of simplicity. But you must always remember that at least the retarded propagator, the kind we have written here, always has a theta t minus ti factor in front of it. Now there does happen to be one case where this propagator is pretty easy to calculate. Easy, of course, is a relative term, and that is the very simple case of a free particle propagator. We will later on calculate the free particle propagator using the path integral technique, and at that point the calculation will be somewhat more complicated than what we are going to do now. And so it's also important that we have at least one check. If we have calculated it using more elementary methods and we already know the answer, we have the advantage that once we get the path integral technique down and calculate the free particle propagator using that, we can be sure that we have got the right answer. So let's try to calculate the free particle propagator, essentially using the ideas that we just described. The idea of expanding in energy eigenfunctions. Now for free particles, let me just start a new page here. Now for a free particle, The Hamiltonian is just minus h cross square by twice m del 2 del x2. There's no potential energy term, and that's nothing but the momentum operator p squared by twice m. Okay, so in this case, the Hamiltonian eigenfunctions are also momentum eigenfunctions. So expanding in Hamiltonian eigenfunctions essentially becomes expanding in momentum eigenfunctions, which is basically using the momentum representation for wave functions. We all know how to do that. A position wave function psi x, let's say ti, at the initial time, can be written down in terms of the momentum wave functions in this very familiar expansion. This phi is a momentum wave function, phi of p, times e to the I px by h cross dp. This is, of course, nothing but a Fourier transform, the familiar Fourier transform that people use in maths and engineering. But in this case, it has this additional significance that this is really an expansion in terms of momentum eigenfunctions, which are the e to the I px by h cross. So you also know that given this particular form, you can find out phi p by doing the inverse Fourier transform, which is really nothing more than integrating after multiplying by phi n star. So this is what comes out here. This is an integral over x now. Of course, the limits of both these integrals are from minus infinity to plus infinity. Okay, now that we have an expansion of psi x ti, the initial psi x, in terms of the momentum wave functions, and we also know how to expand the momentum wave functions in terms of the initial wave function, let's use them to calculate what psi xt is going to be. Well, that's straightforward. It's going to be exactly similar to what psi xti was, namely this phi p e to the I px by h cross times this factor e to the minus I p square by twice m t minus ti by h cross, an integral of over p. Let me just explain what happened here right now. If you omit this factor, what you have is nothing but psi of x at ti. But how will such a system evolve in time? The momentum eigenfunctions, of course, are also energy eigenfunctions, and as time goes by, they will evolve by picking up a phase factor. The phase factor given by e to the minus I times the time interval times energy by h cross. So the energy is just p square by twice m, and that's all we have put back here. Okay, now that we have this, we can of course put back the wave function psi of x ti here by just using the inverse Fourier transform that we wrote down just above. So this is what we are going to do. We are going to use this expression to replace phi of p here in terms of psi of x ti. So what will happen? The integral will turn out to be this. Let me just change the pen color a bit so that I can. The integral will become 1 over 2 pi h cross. Now there's this integral over p, but inside it you have an integral over the spatial variable. But what's important once again is that I cannot call that spatial variable of integration x, I have to call it x prime, just to distinguish it from the x which is sitting here. So this will be integral over x prime of psi of x prime ti. I'm just writing down whatever is here, except that I've replaced the dummy variable of integration everywhere by x prime. Sorry, not xi. X prime by h cross dx prime. So that's the integral over x prime written down. This is, of course, phi of p. The rest of the factors have to be put in into the I px by h cross. And this really is x, the same x as on the left hand side. with a minus I p square by twice m t minus ti over h cross. An integral, of course, with respect to p. So this is the integral that we have to do. But now we have already seen what we should do in the last general case. All we need to do is interchange the two integrals. Here we have an integral over x prime being done first and then an integral over p. If we alter the order in which these integrals are being done, you have an integral over x prime to be done later and an integral over p to be done first. And of course, when you're integrating over p, psi of x prime ti, which is independent of the p, can come out of that integral. And dx prime, this is the integral over x prime being done later. And inside the bracket here, you have the integral over p. Okay, let me just use a slightly different color for this, just to make it easier to see what's going on there. So inside I'm going to write the integral over p in blue, and what we will have is 1 over 2 pi h cross, which is a factor which of course is there from outside. So I've just moved it in. Then we have to the minus I p square by twice m t minus ti, twice m h cross, to the ip. Well, you have an x by h cross outside, you have it is a minus ip x prime by h cross inside the original bracket. So now that you are moving all of the p dependence terms in, you get x minus x prime by h cross t. So it's now very easy to see that this is exactly of the form integral of psi x prime ti times the propagator k x t x prime ti over x prime, and this helps us to read off k x t x prime ti in a very straightforward fashion. Just by looking at the part in blue in the expression above, I can write down that this, of course, this integral was from minus infinity to plus infinity, and what I have is it's a minus I t minus ti by 2m h cross p square, the I x minus x prime by h cross p dp. So this is the integral I now have to evaluate. But this integral is really one of the most familiar integrals to most of you. This is a standard Gaussian integral. Well, almost a standard Gaussian integral. Recall that a Gaussian integral, the standard one that you have all studied, is of this form. Minus infinity to plus infinity to the power minus ax square plus bx plus c dx is simply given by root over pi over a e to the power b square by 4a plus c. But there's one catch here. For this integral to be well defined, you have to make a demand, and the demand is the real part of the parameter a must be positive. It's easy to see why, because only if a has a positive real part does the integrand, the exponential function here, die out fast enough at infinity, at both plus infinity and minus infinity. If the integrand had a negative real part, it would actually blow up at plus minus infinity. If it had a zero real part, well, it will not really fall off fast enough for the integral to be defined. And that is why I refer to the integral that we have to do. This integral up here, which helps us to calculate the propagator, as almost a Gaussian integral. The one problem is, if you notice carefully, the coefficient of p square here, p square of course plays the same role as x square in this formula. The coefficient of p square here does have a minus sign in front, but the a, the coefficient which is sitting here, is actually purely imaginary. It has no real part whatsoever. So what that means is that unfortunately for us, this integral is not really well defined as it is written. Now, such things happen in physics all the time, and we usually find a way out. And the way out we have in this particular case, if you want to do it formally, is to actually just pretend that there is an additional thing here. In addition to whatever you have, there's one more additional piece, a plus epsilon. Remember, there's a minus sign outside, so when you put a plus epsilon inside the bracket and you assume this epsilon is a positive real number, which at the end of your calculation you're going to take to 0. So the presence of the positive real part epsilon actually allows us to calculate the integral, which you're seeing here, using the standard Gaussian integral formula. And once the result has been calculated, we will take the limit as epsilon goes to 0 plus. That's important. It's not really the limit as epsilon goes to 0. It's the limit as epsilon goes to 0 from the positive direction, because only in that case will the modified integral, after you have put in the plus epsilon, be well defined. So if you carry out the trick, the result is going to be pretty straightforward. You can easily calculate what kxt x prime ti is going to be. After you do the substitution, you will have a 1 by 2 pi h cross, which was outside. Then you will have a root over pi by a. So you will have a I t minus ti downstairs, a 2m h cross upstairs. I'm assuming that I've already done the calculation and then put epsilon to 0. So I can't see the trace of epsilon any longer in this expression. And then we have an exponential of b square. B square, of course, is the square of this quantity, which is already as an I. So with the square, you have a minus sign. X minus x prime whole square by h cross square. And 4 times a. So there's a 4, and a will become I times t minus ti, and you have a 2mh cross in the numerator. So that is your integral done for you. Well, we are at our final result, at least for the free particle propagator, but it may be useful to rewrite this a bit by cancelling out various factors and so on. In fact, I can move the 2 pi h cross inside the integral and write this as m over I into 2 pi h cross t minus ti. And what's even more interesting is this exponential factor ultimately works out to be I. The 1 by I going upstairs becomes minus plus I. And then you have a factor which should become pretty familiar as I write it out. After all the calculations done, you get m by 2 x minus x prime whole square by t minus ti. This whole thing divided by an extra h cross. Now this m by 2 x minus x prime whole square by t minus ti, this should be something familiar. In fact, if you had t minus ti whole square in the denominator, then it's easy to recognize that x minus x prime by t minus t prime is nothing but the velocity of a particle which travels from the point x prime at time ti to the point x at time t. So then this would have been simply half times mass times the velocity squared, namely the kinetic energy, or just the energy in this case. Of course, this is actually the kinetic energy times the time interval, which for a free particle is nothing other than the classical action. Action, remember, is the integral of the Lagrangian over time, and because for a free particle the Lagrangian is simply equal to the kinetic energy, which is a constant as time goes by. So this expression that we have here, apart from the I by h cross in front, is nothing but the classical action for the path which takes you from x prime ti to xt. Now it so happens that the action or the classical action for a particular path plays a very, very important role in the theory of propagators. In fact, it's going to play a central role in the path integral formalism, and we can see a hint of that here. Of course, this is a very special result and a very simple one, basically because this is a free particle system, and here the propagator essentially is exponential I by h cross times the classical action. We will see that in most situations you will have modifications from the classical action in the formula, but the classical action, or at least the action function, does play an important role in the theory of path integrals in general, and we are going to see that very soon. Before we end today, let us take another look at the formula that we had derived for the propagator in terms of the energy eigenfunctions and eigenvalues. What I'm going to do is I'm going to write this expression in the bracket form. So I'm going to basically bracket the propagator. Because for this to make sense, I have to supply the C which Dirac omitted when he brought in his notation. So what we are going to do is essentially write the expression on the right hand side of the propagator expression using the bracket notation. Just to remind you, the wave function phi n x is nothing but the overlap of the eigenket phi n with the position eigenket x. X, of course, is a eigenket of the position operator corresponding to eigenvalue, just the number x. So what we are going to use these position eigenkets to express the wave functions in terms of the abstract eigenkets of the Hamiltonian operator. So phi n x in this expression here is nothing but x phi n, and phi n star x prime, the conjugate, as you all know, is simply this. Again a bracket, but in the opposite order. So substituting these two in our original expression, what we get is kxt x prime ti, the propagator, is actually a sum over all n, and then comes phi n star x prime, which is phi n x prime, and then comes phi n x, which is of course x phi n, and we have this energy term e to the minus IEN T minus Ti over H cross. So far, so good. However, it will become even better if we could rewrite the expression in such a way that the exponential terms, which depend on n, go away, and you are left with something simpler. Let's see what we can do about that. With this x phi n, what we can do is in between the x and phi n, the ket and the bra and the ket, in between, what I can do is put in the minus I ht by h cross. Well, because phi n is an eigenstate of h, the Hamiltonian, corresponding to the eigenvalue En, this will naturally give rise to this exponent term e to the minus I En t by h cross here. Along the same lines, you can get the plus IENTI by h cross from phi n, the bra, simply by, okay, this is really not what I wanted to do. This is of course the factor, but what we want to do is, instead of putting En here, if I just erase out the En carefully and insert in its place the Hamiltonian, then I'm nearly done. Then I actually have an expression where the only n dependence is in the kets and bras here. And this actually has a huge advantage, as you will soon see. Then of course we write this in this form, x You can move the sum over n inside here because the only independence is in phi n and the phi n. So what I've done is I've just moved these two, switched the position of these two so that the two phi n sit next to each other. But once you do that, you can see what I'm driving at. I will be left with the fact that this thing in here is nothing but the identity. That's the closure relationship between energy eigenkets, and this means that the propagator is nothing but the matrix element between the states x and x prime, between the position eigenstates x and x prime of this quantity. Now this particular operator which is sitting between x and x prime should be pretty familiar to most of you. This is the so-called time evolution operator in quantum mechanics. It tells you how a state evolves in time from time ti to time t. Another way of looking at the propagator is that it is nothing but the matrix element between the position eigenstates x and x prime of the time evolution operator. That's one way of looking at it. Another way of looking at it would be you could use the time evolution operator to define time-dependent position eigenkets. Now, how can a position eigenket be time-dependent? Well, it can't, right? Because position operators don't depend on time. So how could the eigenkets depend on time? But then, recall that position operator does not depend on time in the Schrödinger picture. Whereas if you went to the Heisenberg picture, the position operator would actually depend on time. And so its eigenkets, of course, will also depend on time. And the next day we will start from that. We will show that in the Heisenberg picture, this can be thought of as a position eigenvector corresponding to the eigenvalue x at time t and overlapped with the position eigenvector with eigenvalue x prime at the time ti. So next day we will derive this expression by explaining how to go to the Heisenberg picture from the Schrödinger picture. Many of you already know this, but maybe a recapitulation would be useful. And then we will use that and a few small steps in between to derive the path integral representation. Okay. Until then, goodbye.